In this video, we're going to talk about heterobenzenes. Um, Heterobenzenes are often called heteroaromatic compounds, but typically we call them heterobenzenes for short. And essentially, a heteroaromatic compound is an aromatic compound that contains one heteroatom, so like nitrogen, oxygen, sulfur, and so on. A common example of a heterobenzene is pyridine. Here you see pyridine, which you have seen before. I hope this rings a bell. Um, and it looks like benzene, except nitrogen is replacing one of the carbon atoms in the ring, and it has a lone pair of electrons on the nitrogen. And so we call this pyridine. One of the questions that we have to think about in terms of aromaticity is we see that there are 3 double bonds. Each double bond constitutes 2 electrons, and so there are 6 electrons in that ring. And the nitrogen also has a pair of electrons on it. And so we have to always ask ourselves, are these electrons part of the pi system? Now, the answer to that is no. They're not. And the reason for this is because the nitrogen in this case is sp2 hybridized. It has a p orbital in which there is already a pi bond being formed with that p orbital, and so the electrons in the lone pair of electrons actually reside in an sp2 orbital. And if we take a look at the shape of pyridine, and we think about those p orbitals, we can draw the p orbitals of all of the carbons, we can draw the p orbital of the nitrogen, and then we have this sp2 hybridized orbital of nitrogen that is perpendicular to the p orbitals. So here we have an sp2 orbital. And if we think about the electrons in this system, we know we have the 6 electrons in the ring, and then the 2 electrons in the sp2 orbital. And you see that those 2 electrons are not part of the pi system. And so there are only 6 pi electrons, right? And because of this, we have a cyclic, a planar, a fully conjugated ring that has 6 pi electrons, which satisfies Huckel's rule. Now, there are also 5-membered heterobenzenes that are aromatic as well. The most common one in this case so here I have a 5-membered ring with a nitrogen. I can have a 5-membered ring with an oxygen, or I can have a 5-membered ring with a sulfur. So the 5-membered ring with the nitrogen is called pyrrole. The 5-membered ring with oxygen is called furan, and the one with sulfur is called thiophene. So pyrrole, furan, and thiophene. These are common 5-membered ring heteroatomic aromatic compounds. And you might be asking yourself, well, how are they aromatic? Right? And of course, in order to be aromatic, they have to satisfy all 4 of our rules. So let's take a look at pyrrole. Again, in the case of pyrrole, I have 4 electrons from the pi system, the 2 double bonds, right? And so if I think about this particular system, the nitrogen here, we would, if you look closely at it, there's no double bond on that nitrogen. And so at first glance, it would appear that it's sp3 hybridized. And yet, with heteroatoms, if the hybridization can change to sp2 hybridized, then we know that there's a p orbital available. And indeed, that's the case. We know that because pyrrole is planar, trigonal planar. That nitrogen is trigonal planar. And so it has a p orbital available to it. And in that p orbital, we have the 2 electrons. So we have that pair of electrons um, on the nitrogen that's in a p orbital, not an sp2 orbital, right? So the nitrogen-hydrogen bond is it's a sigma bond from a sp2 orbital. In this case, you see that it's fully conjugated, right? Assuming the nitrogen is sp2 hybridized, which it has to be because it's planar, it's trigonal planar. It's cyclic, and now it has 6 pi electrons, right? The 4 from the carbons, the 2 from the nitrogen. And therefore, it has the same number of pi electrons as benzene does and as pyridine does, and therefore it is aromatic. And we can do the same thing for furan as well. Again, all of the carbons obviously are sp2 hybridized. The oxygen, we would assume at first glance is sp3 hybridized, but again, the structure tells us differently. Furan is a planar structure, right? And the oxygen, if it is sp2 hybridized, then it has a p orbital and it has an sp2 orbital. In the p orbital, right, there has to be 2 electrons in both the sp2 orbital and then 2 electrons in the p orbital. So one of the pair of electrons resides in the sp2 orbital, one of the pair of electrons resides in the p orbital. And again, if we're counting pi electrons, right, then that gives us 6 pi electrons. And we can do the same thing for thiophene as well. Thiophene and furan have similar properties. So now we can think about some acid and base properties of heterobenzenes. And when I look at pyridine, pyridine is an amine. It's an aromatic amine. We know that amines are fairly basic. And so pyridine is basic. It's not as basic as normal aliphatic amines, and the reason for that is because the nitrogen is sp2 hybridized, and so we've seen that sp2 hybridized atoms can hold on to their electrons a little bit tighter, and therefore the basicity should decrease. But we can react pyridine with an acid like hydrochloric acid. The lone pair of electrons attacks the proton. That hydrogen-chlorine bond breaks, the electrons go to the chlorine, and we end up with this structure, right? And this structure is called pyridinium chloride. Pyridinium chloride. And we can actually determine the relative basicity of pyridine by looking at its conjugate acid. And if I think about the conjugate acid, this pyridinium chloride, we see that its pKa is 5.2. And so it's, in terms of acidity, it's not a very strong base, and so we have kind of a not very strong, it's a somewhat of a weak base, and so, but not a really weak base, and so the pyridine is kind of in the middle in terms of its basicity. Notice when pyridine adds a proton, the aromaticity of the ring isn't affected, and so pyridinium chloride is also aromatic as well, right? Because the lone pair of electrons aren't part of the aromatic ring. When we look at pyrrole, we see pyrrole has very different basicity properties. And in fact, I go to some extent in saying that it's not basic at all. And the reason for this is because if we think about the electrons, right, that we would kind of initially think about in terms of donating, they would be on that nitrogen. But remember, those electrons on pyrrole are part of the pi system. And therefore, if we use those in terms of reacting with an electrophile, we could potentially lose the aromaticity. And in fact, when pyrrole reacts with an acid like hydrochloric acid. It does so by donating that pair of electrons into the ring, and then a pi bond actually attacks the acid, right? And you get this structure. Now this is still not favored, right? This would be the conjugate acid of pyrrole. And you see that the pKa is -4, so it is a very, very strong acid, which means that pyrrole is a very, very weak base. And so the equilibrium is definitely going to lie to the left. The reason for this, obviously, is because now in this particular case, we don't have an aromatic compound. So the conjugate acid is not aromatic. And so that aromatic stabilization really is the cause of pyrrole not being very basic at all. However, pyrrole is somewhat acidic. And if we take a look at pyrrole as an acid, its pK is 23. Now, you know, how does this compare to other acids? Well, remember, alcohols have about a pK of about 16 to 19. Water has a pK of 15.7. Alkynes have a pKa of about 25. So it's a little bit more acidic than alkynes. And we can treat it with a very strong base like an amide or LDA, and we can deprotonate it. And the result is this anion. And so what I want you to notice is this anion is still aromatic. One of the pair of electrons is part of the aromatic system. The other pair of electrons is in an sp2 orbital, and therefore aromaticity is retained. Now, one of the things, the last thing that I want to talk about in this video is how pyridine can behave as a nucleophile. We saw that it can behave as a base. It also can behave as a nucleophile as well. And so it will undergo nucleophilic substitution reactions. I can react pyridine with an alkyl halide. Here I have pyridine reacting with ethyl bromide. I get a substitution to occur, and the result is this. So notice the nitrogen now has a positive charge. I form a salt, and it's very similar to when it reacts with HCl, right? It's a nucleophile, HCl is an electrophile. Here pyridine is a nucleophile, ethyl bromide is an electrophile. And the result is a salt. And so this particular salt is called ethyl pyridinium bromide. We also see that we can oxidize the nitrogen on the pyridine ring. So if I take pyridine and I react it with hydrogen peroxide in acetic acid at 75, so heating this up at 75 degrees Celsius, I get this, right? So it's a type of substitution reaction where oxygen is substituted onto the nitrogen, and these are called pyridine N oxides.